Seconds, audio kicks in, should be good to go. So today is Tuesday, a little shorter video lecture on radiometric dating today. Yesterday we got through our, rates of decay, or start rates of radioactive decay, some different new equations, did the fatal dose of bananas homework, talked through that. Reminder about these chapter 19 book questions. Today, this lecture a little shorter. If you finish it today, it's fine. Even if you would want to save it for tomorrow, I wouldn't really care. Wednesday's kind of a work day, but most of you probably just want to get the video lecture done, view and take these notes. Tomorrow's a work day. Finish that lecture if needed. Get review for the quiz. I'm available for the work day. If you got questions, just let me know. You could be working on the chapter 19 book questions, and then Thursday we'll do our quiz on half-lives, radioactive decay, etc., and the equations. And today I'll have the cutoff point for the quiz in the lecture today that we get through. And then we'll have another lecture that I'll get to you ultimately on for Thursday. And then we'll meet as a team on Friday live and go over this quiz and talk more about sort of nuclear fission and get into fission/fusion at the tail end of this week and beginning of next week. So that's sort of the plan. You guys saw this. We're kind of starting that plan. Obviously, it's Tuesday, and we'll get going. So with that, today's video lecture, I want to talk a little bit about radiometric dating and specifically like radiocarbon dating. Now, radiocarbon dating is a specific type of radiometric dating. What does it revolve around? What is it sort of referencing? It's using radioactive isotopes to be able to ultimately age how old a sample or a substance is. Okay, so we can use the rate of decay and knowing the half-life of these different radioisotopes to determine how the age of different substances. So carbon-14 is a really common example of a type of radiometric dating called radiocarbon dating, or a lot of times it's called carbon dating or carbon-14 dating. So, you'll hear about, some archaeologists will unearth this, ancient culture or whatever. They'll find some artifacts and they will, they're able to say, well, these people existed here, 27,000 years ago or whatever, or 18,000 years ago or 11,000, whatever, right? How are they able to do that? What does it revolve from? They use carbon-14. Carbon-14 is a naturally occurring radioactive isotope of carbon. It is the result of cosmic radiation colliding with nitrogen in our atmosphere. So we talked a little bit about this before. It has carbon-14 has a half-life of 5,730 years. And this nitrogen-14, when it bombards from when nitrogen collides with neutrons from cosmic radiation sources. Remember, we talked about our planet is barraged with various forms of cosmic radiation all the time. There's lots of nitrogen gas in our atmosphere. Our atmosphere is over 70% nitrogen gas. Some of that nitrogen gets converted into then carbon-14, okay? Well, carbon-14 is present in carbon dioxide, okay? So atmospheric carbon and carbon dioxide then is used by plants and photosynthetic organisms as part of the process of photosynthesis. So eventually, right, this carbon dioxide that contains a certain amount of carbon-14 ends up in plant tissues, and those plant tissues then get consumed by other primary, secondary, tertiary consumers, and then we have carbon-14 present within the tissues of plants, within the tissues of all other organisms and animals. So there is a certain amount of carbon-14 within our bodies, okay, because of this balance within atmospheric carbon dioxide, okay. So the interesting part about it is with the half-life of carbon-14, and this is part of the reason why they sort of choose this amount, new carbon-14 is produced at about the same rate as it decays. So in other words, in our atmosphere, there is this balance of how much carbon-14 is present versus how much carbon-12 is present. It's always constant, okay? And because consumers are always constantly consuming material and replacing dead and decaying tissue or replacing tissues within our bodies, plants are constantly pulling carbon dioxide out of the atmosphere. This ratio of constancy or balance between carbon-12, which is the most common isotope of carbon, and carbon-14, which is a radioactive isotope, is constant not only within our atmosphere, but it's also constant within the tissues of living organisms, right? So living organisms are constantly replacing carbon within our bodies through the foods that we consume. So in our bodies right now, we have the same balance of carbon-14 to carbon-12 as what we see in the atmosphere because of us constantly replacing those, okay? So CO2 is used by plants in photosynthesis. We've said this. The amount of carbon-14 in living plants and animals is constant, right? But, right, so here's the deal, right? The statement is that when a plant or an animal or any sort of organic living organism dies, the radioactive decay continues. So whatever carbon-14 was present in that sort of balance between carbon-14 and carbon-12, well, that organism, right, when it dies, no, it's no longer fixing carbon dioxide if you're a plant into plant tissues. It's no longer consuming macromolecules and replacing carbon atoms within our bodies. You know, when animals die, when we die, we're no longer replacing any sort of carbon within our bodies. So the carbon-14 that is present within organic materials, carbon-containing compounds, starts to decay. So the decay continues though, right? So the carbon-14 now is going to decay and go through various half-lives over time, right? So we can, by looking at the rate of decay, you can determine the age of the organic material. So if we find, you know, like I said, this archaeological dig, and we find some, you know, maybe it's some plant or animal remains, or maybe it's some actual remains of the humans that existed there, or any sort of, you know, maybe it's even a piece of clay pottery that has plant material in it, that we can isolate and look at the amount of carbon-14 that exists there. We can use that to determine the age of that material, right? Because, right, carbon-14 will go through beta decay. So carbon-14 will go through beta decay back into nitrogen-14, most common isotope of nitrogen, and give off beta particles. Now, the half-life, we said, of carbon-14 is that of 5,730 years, okay? So it does put some limits to how much we can actually sort of use carbon-14 as a way to date the age of substances. So it's accurate only to about between 7,000 to 30,000 years. Now I want to put some perspective on that. Let me get my calculator out. Calculator. So we said 5,730 years is the half-life. So 30,000 years, 30,000, 3, divide that by 5,730, that equals, you know, a little over 5 half-lives, right? Now, the reason why that is, and the reason why we can only use carbon-14 dating for a limited amount of, you know, a window of time, maximum of about 30,000 years, you couldn't use carbon-14 dating to identify the age of, you know, some sort of cephalopod that existed 550 million years ago. It doesn't work like that, because at that point there is such a small amount, okay? Remember when we talked about this, I'm gonna go back, give me a second. Radioactive decay, right? Goes through these series of half-lives. Remember we said after about, you know, when you get past kind of 4 or 5 half-lives, no matter kind of how much you start with, you're going to have such an infinitesimally small amount of it. So because carbon has a limit, you know, a 5,730 year half-life, you know, you get past 5 half-lives, no matter what you kind of start with, you're going to have such a small amount of it. And if you've got such a small amount of it down here, once you get 4, 5, 6, 7 half-lives, it's, with various measuring devices, it's nearly impossible to actually get a reading to see how much beta decay it's actually giving off, okay? So this is the reason why there is sort of a set range with carbon-14 in terms of how it can actually be used or applied, okay? Now you might ask, well, how do they know like this, like cephalopods that existed 550 million years ago? How do they know that is how the age at which those, those fossils or those materials existed? Well, you can use different radioactive isotopes. One that's kind of commonly used is like potassium, different radioactive isotopes of potassium. Potassium is a common element that exists in rocks and various rocks and minerals. Well, you can look at rock layers from millions of years ago, and you can look at the rate of decay from the potassium that exists there to be able to determine the age of that particular sample. Okay, so this is how in the geologic record they've been able to assemble kind of the fossil record and figure out what times did these things exist. Not just relatively, but actually can put dates on it by using different radioactive isotopes, because these different radioactive isotopes that have longer half-lives expand really this range deeper and deeper into time, right? So pretty cool. Radioactive isotopes can be used to be able to, the process in which they decay can actually be physically used to determine the age of a substance, right? So it's pretty neat. All right. So we're going to look at kind of an example where we kind of, I think we introduced this a little bit yesterday. This idea of activity. Sorry, I'm pausing a little bit. I need some coffee. But we're going to look at this combination of this equation, the activity equation, times the rates constant times the number of atoms present, and then using this ratio of the activity of the substance at time 0 to the activity of the substance at time t, which is sort of now. And then remember, the rate constant is calculated by taking, what is it, 0.693 times the half-life, right? So, right, so this equation where we talked about activity, this is sort of looking at the activity or radioactive decay of a substance at any given sort of snapshot in time. But we can use its rate of decay and to develop this ratio to ultimately determine how old the substance is, the time or the age of that substance, by looking at the natural log of this ratio, multiplying or using that in combination with the rate constant to determine the age of the substance. So we know, right, we know the activity of, if we know the activity of that substance at time 0, and we're going to look at an example that uses carbon-14 dating, we know the activity of organic compounds that come from living things because we can measure that. We can go up and measure you with a Geiger counter, and we can determine how much beta decay is being given off by you from carbon-14. And then we can take a sample of, say, dead or decay material that we're trying to get a date on, and we can measure its activity at time now. We can use that then, right, to determine how old that substance is. So this is the equation we're primarily using, but it comes from activity and this idea of rate of decay and the activity equation that we worked on yesterday, right? So this is an example problem, and I'm just going to tell you flat out, this is an example problem out of chapter 19 in your book. It talks about like the Dead Sea Scrolls, and it's a piece of paper from an ancient scroll is found to have an activity per gram of carbon of 10.8 atoms per minute. So its activity units right now at this time is 10.8 atoms per minute. So every minute about 10.8 atoms of carbon are going to be going through carbon or decay, right? So carbon is going through beta decay, and at this particular point in time, that we found this ancient scroll that contains paper, and paper is a plant product. It's got 10.8 atmospheres per minute as its activity. Now, carbon-14 in living organisms and in organisms that are alive, really, the activity of carbon-14 beta decay is 13.6 atoms per minute. Okay, so the activity at time 0, when that, when the tree or the plant material that was used to make this ancient scroll, this ancient piece of paper, was alive, it was going through a activity of, or rate of decay that was giving off an activity of 13.6 atoms per minute. Now, through time, it has gone down, because naturally it's going to, because carbon is going through half-lives every 5,730 years, and you have less and less of it. We are going to estimate the age of this ancient scroll, right? And we're going to use this by using this equation. So our primary job here is that we got to establish the rate constant, okay? And then we're going to plug in, ultimately, the activity for time 0, which we were given, and the activity for time t, which is now, and time t is how old this scroll is, okay? So that is going to be our job coming up. All right, so we're using this equation, and what do we have to plug in? So the activity units that were given to you from us from this scenario, the activity units for time 0 is 13.6 atoms per minute. The activity for time t is 10.8 atoms per minute. We have to calculate our rate constant. We're going to take the rate constant is 0.693 divided by the half-life. Well, again, carbon-14 is 5,730 years, so 0.693 divided by 5,730 years gives me this value of the 0.000121 over years. Okay. Now, notice some things, right? We're solving for t, right? So this is the variable that we're solving for. Now, we take the atoms over minutes are going to cancel. So we take the natural log of 13.6 over 10.8, and that will give you the 0.2305. So again, it becomes a unitless number on this side. We got 0.00121 over years. In order for me to solve for t and get to t by itself, I got to divide both sides by the 0.00121. That gets rid of it on this side, right? And it's going to get t by itself, which is what we want. Now, when I do that, right, okay, what does that ultimately result in? I want to, again, make a point. Okay, sorry, I got to get my marker back. If I take 0.2305, divide that by 0.00121, that gives me 1,905 years, right? So the age of this scroll is 1,905 years, but I want to prove to you the units, right? Well, over here, what do we got? We've got 1 over, right? And this is 1 over years, okay? So we've heard this before, right? So 1 over years. Anything dividing by a fraction is the same as multiplying by its reciprocal. So it's the same as me saying 1 times years over 1, right? So, well, 1 times years over 1 is years. So that, again, gets us into the units. And the units are that of, in this case, the half-life of carbon, right? So this ancient scroll is just a hair, just a little bit under 2,000 years old. That's really old, right? From kind of human standards, and especially for, you think about like a scroll or a piece of paper, for it to survive that long is remarkable. Now, some things to kind of keep in mind, like in sort of using this equation, right? And I know we looked at the other sort of version of this with the XO over X. Keep in mind, like, if we were to ask this sort of backwards, let's say I gave, I know how old the substance is. I know its half-life, and I know its original activity. I can actually determine the activity of it right now by working backwards. But remember that to get rid of the natural log, you got to use the e to the x key, okay, in order to be able to do that. So in order to solve for, something that's embedded within this statement on this side to get rid of the natural log statement, you got to use the e to the x key. So that's referencing kind of what we talked about in class yesterday, right? So maybe a little less typical kind of problem type that is using this equation, but pretty cool, right? Like we are able to take and use, a process, this process of decay, knowing the half-life of a substance to be able to determine how old a substance is. And this has been used in science and geology to be able to discover a heck of a lot about how our planet has changed and evolved over time by using radioactive decay as a means of being able to test this and understand that. So pretty cool. All right, so that does wrap it up. Like I said, short, a little shorter video, not too long. This marks the quiz cutoff point, and is the end of today's lecture. Remember, you guys, you'll watch this today, finish it tomorrow if you need to. Work on reviewing for the quiz, work on those chapter 19 book questions. I'm not really sure exactly where we're at within this sequence. There's not a whole lot of them, guys, which is kind of nice. But working on these are great as we're kind of moving our way through this particular unit. And then again, Thursday will be our quiz, and we'll do the same thing. I will email you that quiz at the beginning of class, and then you guys need to email it back to me before the end of class. All right, that is it, guys. We'll see you later. Goodbye.